The last time we spoke about one process that applied to all three types of modeling. What was that? Anyone? Sensitivity analysis, right? Assessing the degree to which our model results are contingent on our assumptions, right? We spoke about several types of sensitivity analysis. Anyone remind us? What are simple types? Stochastic, good, awesome. Structural sensitive analysis, where we reflecting the fact that it's really structured considerably more so, a lot more so than parameter values that shapes what behavior is possible in a model. How it could within some ranges, how it could possibly behave. Can it exhibit oscillations over time? Does the stock of susceptibles just go down, or can it bounce back? To what degree is there a systematic approach to an equilibrium, etc.? These are functions of stochastics, and stochastic sensitivity analysis lets us probe if we alter that structure, like adding an additional flow for loss of immunity, for example, or assuming that there are asymptomatic people beyond symptomatic spreaders of infection. How does that alter our assumptions? Again, we're seeing the degree to which our results are contingent upon our assumptions of structure. What's another type of sensitivity analysis that we can have? Yes, yeah.
There's no one for like that.
So I would count all of these as dynamic models. You maybe think about stochastic sensitivity analysis, which is about dynamics over time. But the truth is, you can actually do some sort of dynamic sensitivity analysis where you basically drive the model with a function, maybe assuming immigration goes up over time, or there's a new introduction of a variant of concern for COVID at a certain time, and what happens then. So sometimes we might view certain types of scenarios as a form of sensitivity analysis. So that much is true. Anyone else want to next one? Yes. So Francisco.
Instead of like taking the structure of the model, we be able to like vary parameters.
Vary parameters. Yeah. One way or multi-way at the same time. Yeah. Now, one thing I didn't emphasize last time, and I stand to be correct, is this is an important point. When we talk about sensitivity analysis, there's an important question. So we're seeing the degree to which our conclusions are contingent on our assumptions, but what are we examining as indicative of our conclusions? Are we looking at specific outputs, number of people infected? Or are we looking at our decisions about whether one policy A is better than policy B? It may be that, as we vary our assumptions about parameters, that it changes quite, in some way. For maybe this is policy A, choice A we have. And maybe this is parameter set. So parameter vector, often we describe it as a vector of parameters. So this might be C, this might be beta, this might be tau, the length of infection, this might be, the mean, this might be the mean time cell loss, or the rate at which people lose immunity. This is what's called parameter vector. For any one run of the model, we might have a particular value here, particular value here, particular value here. Does that make sense? So we run the model with a particular, I say set of parameters, but it's really it's a particular mapping of parameter value a parameter omega has this value. Tau has this value, right? C has this value. And we often put it in a vector where the exact index assumed by a given parameter C is not as important as what the value is for it. So, maybe we write it with C being, 10 people per day and beta being 0.04 and tau being 10 days and omega being 1% per day. That would be one parameter, right? For a given scenario. You comfortable with that? Good. Looking at least control is number 16. This is a parameter vector. Okay. And so a given policy might be kind of certain parameter vector for that policy, and maybe by default, but maybe as we alter our assumptions about the contact rate, we find policy A. So this might be parameter vector 1, and this is policy A with parameter vector 2 with a different assumption about C, right? And you might say, wow, that's a big change. And that's true. It could be a big change. But maybe what we're really interested in is policy A bigger, better at some level. So maybe this is cumulative infections that occur while we run the model over time, right? You describe graphs, good to describe what's at one axis, other axis. So this might be over time. Policy A with our default parameters gives this result in terms of cumulative number of infections that have occurred in policy, and with an alternative assumption about our policy sensitivity analysis with a different assumption about, so maybe this is PB1 and maybe PB2 has 12 people per day, but everything else is maybe the same, right? And so this might be PB prime or PB1, PB2. There we go. So you get that point that assuming different parameters, we get to higher on this 8.0, it might lower the number of cumulative infections. You get that point with a sensitivity analysis. Now, maybe though for policy B, if we run it with our default assumption for policy B, maybe it yields something like this over time. So this would be policy B. We institute contact rate something with parameter vector 1. And maybe policy B with parameter vector 2 is also a lot different than policy B with parameter vector 1. There's a big difference. But there's an invariant here. There's something that retained. If our goal is comparing, is policy A better in terms of lowering the cumulative cost of infection than policy B, if what we're really interested in is which gives us lower cumulative infections, in both these cases, which is better? To lower the number of infections. Policy B, right? Policy B for assuming parameter vector 2. This alternative assumption is lower than policy A. Assuming the original policy vector, maybe a default one, policy B also yields lower results in policy A, right? Lower cumulative infection. So we might say, regardless of, technically changing that parameter had an impact on the results as measured by cumulative infection. But if what we're interested in at the end of the day is which policy do we prefer, in both cases, it leaves us confident that policy B may be better. Do you understand that point? And this is a really important point with modeling. People get all tangled up sometimes. You don't know what the parameter is. You don't know what the three values of these parameters are. And that's true. We're often dealing. The cards we're dealt has us unsure about what the values of parameters are. That may well be true, but it may be that the difference between two policies, as we change assumptions about those parameters, the difference between two policies is conserved, or at least it's consistent in preferring one to the other. And that lowers our vulnerability, our exposure to just saying, you can't say anything out of this model. Often you can say things. You have to pick the outcome that's of interest to you, and sometimes you find the results sustain that outcome and saying this one is preferred to that one. Do you get that point? So at some level, our results are changing with parameters, but the result that we care about the most, that A is better, that B is better than A, or what have you, which is better, that one it's robust. Do you get that point? This is a subtle point. And often you find that people who have never encountered dynamic modeling before say, well, you can't model if you don't know what the values of the parameters are because it will change the result. Yes, but it may not change the results we care about, which policy is better. You understand that? In both cases, did it change the results? Yeah, going from parameter vector 1 to 2 changed the results for policy A. And in a big way, it changed the results for policy B in a big way. What it didn't change is that policy B gives us lower cumulative infections. Do you get that point? No, really important point. And so, at a glib level, it's easy to just say, well, we don't know what the result is. It will change if we change parameter vectors. Yes, but the things we care about at the end of the day, the decision makers care about, may be quite robust, given those uncertainties. Okay, important point, something I didn't touch on last. Any questions about that? Okay, so that's good. We've hit on some key points of sensitivity analysis that I hadn't hit on before.